Welcome children. Today we are going to see about numbers and sequences. In that you have an important theorem that is called Euclid's division lemma. So lemma is actually a mini theorem only. So you take page number 38, Euclid's division lemma. Let A and B be any two positive integers, then there exist unique integers and or such that A is equal to BQ plus R. Okay. So here this is A is equal to BQ plus R. This is called the Euclid's division lemma. Now turn to page number 39, example 2.2. So here the first sum, find the quotient and the remainder when A is divided by B in the following cases. First case is A is equal to minus 12 and B is equal to 5. So according to Euclid's division lemma, A is equal to BQ plus R, where 0 less than or equal to or less than modulus of B. Modulus means plus or minus. Okay. So here what you're going to see is now you can write this minus 12. That is A is equal to what is given there? Minus 12. That is equal to B into B is what is that? 5. 5 into, then you have to put some other number here in the bracket, inside the bracket, plus some other number, so that you will get the answer as minus 12. So if you put minus 3, no, what it is? 5 into minus 3 is minus 15 plus 3. So unlike sign, subtract and put the sign before the greater number. So you'll get minus 12. So what is the value of Q here? Minus 3. And what is the remainder? Remainder is R. So R is equal to 3 and the quotient Q is equal to minus 3. Okay. Now the next is sum. A is equal to 17 and B is equal to minus 3. So by Euclid's division lemma, A is equal to BQ plus R, where 0 less than or equal to R less than modulus of B. So A is equal to, like the previous one, what is our A is here. Now what is our B? So our B is minus 3. So you have to put minus 3 into into Q. That is the quotient plus the remainder. Okay. So into which number you have to put? So here, since it is given as 17, no, A is equal to 17 here. So if I put minus 5, then minus into minus plus 15, then which number you need? Plus 2 you need. So that you will get 17 there. So here you put 17, ma. Instead of A, you put 17. So what is the quotient? The quotient is minus 5 and the remainder is 2. Now the third sum, A is equal to minus 19, B is equal to minus 4. So by Euclid's division lemma, A is equal to BQ plus R. Okay. So what is our A here? Minus 19. What is our B here? Minus 4. Into, you have to put the number Q plus some other number. So since you have minus 4, so minus 4 into 5. If I put minus 4 into 5, it is minus 20. Then plus 1. So minus 20 plus 1 is minus 19. So what is our remainder? Q, 5. What is our quotient? Q. Q is 5 and the remainder is 1. Now the next is sum. That's in page number 40. Example 2.3. Show that the squares of an odd integers is of the form 4q plus r for some integer q. So what we are going to take, let x be an odd integer. Then since any odd integer is 1 more than the even integer, yes, we are taken, for example, if I take 2, 2 is an even number. Okay, if I add 1 to 1 with that, 2 plus 1 is what? 3. 3 is an odd number. So if we add 1 with any even number, you will get an odd number. So we are writing this one, x is equal to 2k. So since we are taken this one, x is an odd number. So how to express x? X is equal to the even number. So even number means multiple of 2. Yes. So 2 into any number will get the even number. 2 into 1, 2 ones are 2, 2 twos are 4 in the same way. So 2k plus 1 plus 1. So that 2 plus 1 is 3. 4 plus 1 is 5. You will get an odd number for some integer k. Now what is our x square? 2k plus 1 the whole square. Now this is of the form a plus b the whole square. It is a square. A square means 2 square. It is 4 k into k square plus 2ab. 2 into 2k into 1. That is 4k plus 1 square is 1. I'll repeat. 2k the whole square is 2 square is 4. K into k is k square plus 2ab. So 2 into 2k into 1. 2 into 2k is what? 4k plus 1 square is 1. Now we are taking this 4k outside for these two terms. If I take 4k outside, only this k will remain. If I take 4k outside, 1 will remain. So k plus 1 plus 1. Now what is q is equal to k into k plus 1. We have taken this one as q. K into k plus 1 is some integer. So it is 4q plus 1. So again, what is our what we are going to prove? So one more thing, let the odd integer of the form 4q plus 1. That is also the square of an odd integer is the form 4q plus 1. Now we got the square of the odd integer is of the form 4q plus 1, where q is equal to k into k plus 1. Okay. Now example 2.4, that's in page number 41. If the highest common factor HCF of 210 and 55 is expressible in the form 5x minus 325, find x. Okay. So by Euclid's division algorithm, let us find the HCF of the given numbers. So you know how to find HCF in this division method, yes? So that you have studied already in 8th standard. Now, here what you are going to prove is, first you take 215. You are going to find out the HCF of 215 and 55. So you divide 210 by 55. How many 55s are there in 210? 3. So 3 into 55. 3 into 55 is what? 165. Plus what's the remainder? That is 45. Okay. Now, after that, what you are going to take? This one, this 55, this quotient. So 55 is equal to, now what's the remainder here? 45. Yes, according to the Euclid's lemma. So this is the quotient PQ plus R, BQ plus R. So here this is the quotient and this one. So here 45. So here the remainder is 45. So this 55 is equal to, now you have to take 55 and 45. Divide 55 by 45. How many times? 45 into 1 plus, what is the remainder? 55 minus 45 is 10. Now you take this 45. 45 equal to, divide 45 by 10. How many 10s are there? 4. What's the remainder? 5. Okay. So if you see here, you can understand more this one. Then what you have to take now? You take this 10. So 10 is equal to, divide 10 by 5. How many 5s are there in 10? 2. What is the remainder? 2 5s are 10. The remainder is 0. So the HCF of 210 and 55 is the last one. This one, last divisor. Here 5. Okay. So now the HCF is expressible in the form, in the sum it is given 55x minus 325. Now we got in the answer, by finding this HCF of 210 and 55, we arrived at the answer 5. Now here in the book it's given, this is equated to 55x minus 325. Now you keep this 55x as it is, bring this minus 325 to the other side, so this becomes 330. X is equal to 330 by 55, you'll get 6 is the answer. Now the next example, that's in page number 42. Example 2.5. Find the greatest number that will divide 445 and 572, leaving remainder 4 and 5 respectively. So that find the greatest number means that is the, find the greatest number means that is nothing but the HCF. Since what is given, you are going to find out the greatest number that will divide 445 and 572, leaving the remainder as 4. So first you subtract 4 from 445. What you will get? 444. Then subtract 5 from 572. Since you are getting the remainder as 4 and 5, that remainders to be subtracted from the given numbers. Okay. So if we subtract, you will get 567. Now we have to find out the HCF of 441 and 567. So by Euclid's division algorithm, we take this 567 and 441. Divide 567 by 441. How many times? One time. What is the remainder? 126. Now you have to take this divisor 441 equal to divide this one by the remainder. Yes, 126. How many times? 126. 3 times. So if you multiply, you'll get 378. The remainder is 63. So 126 into 3 plus 63. Now you have to take this number 126. That is equal to divide 126 by the remainder 63. How many times? 2 times. Plus the remainder is 0. So the HCF of these two numbers is 63. So the required number is 63. Now example 2.6. That's in page number 43. To find the HCF of 396, 504 and 636. So if it comes under this exercise, no, you have to find the HCF using this Euclid's lemma only, division lemma only. So 500 take. First you take 504 and 396. These two numbers you have to take first. Okay. Now first divide this 504 by 396. How many times? Only one time. What is the remainder? 108. Now this divisor you have to take 396. Divide this divisor by the remainder. How many times? 3 times. 108. 3 times plus the remainder is 72. Now you have to take this divisor. This one as a divisor 108. Divide the divisor by the remainder 72. Yes. So how many times? Only one time. So the remainder is 36. Now you have to take this divisor 72 and divide the divisor by the remainder, that is 36, 2 times. So the remainder is 0. So the HCF of 396 and 504 is the last divisor 36. Now one more number you have, that is 636. So you have to find the HCF of these two numbers now. Now divide 636 you take. So this will be 17 times. This 36 is 17 times there. The remainder is 24 there. So the divisor you have to take 36 equal to the remainder 24. Now divide the divisor by the remainder only one time and the remainder is 12. Now you take this, the divisor 24, that is equal to divide the divisor by the remainder. How many times 12 is there? 2 times. The remainder is 0. So the HCF of these three numbers is the last divisor, that is 12. Okay. Now straight away we'll go to the exercise 2.1. That's in page number 43. Exercise 2.1. First is find all positive integers when divided by 3 leaves remainder 2. So here you have to take all positive integers when divided by 3 leaves the remainder 2. Yes. So here how to take, since the given number should be divisible by 3, it should be a multiple of 3 only. 3, 6, 9, 12 like that only. So we have taken this one as 3k and leaves the remainder 2. So this 2 to be added. Okay. It leaves the remainder 2. So this 2 to be added where k is equal to 0, 1, 2, 3. Now when k is equal to 0, if I put 0 here, what is the answer? 2. If k is equal to 1, 3 into 1 plus 2, 3 ones are 3 plus 2 is 5. When k is equal to 2, 3 into 2, 3 twos are 6. 6 plus 2 is 8. Sorry, it's 8. 8. 8 here, 8 comes. 8 ma, not 7, 8. Change it as 8 ma. 3 twos are 6. 6 plus 2 is 8. Change this one as 8 ma. 8. Then when k is equal to 3, 3 into 3, 9 plus 2 is 11. So the numbers are 2, 5, not 7. It is 8, 11, etc. Now the second sum, a man has, this is very, very important sum for your public exam. Second sum, a man has 532 flower pots. He wants to arrange them in rows such that each row contains 21 flower pots. Find the number of completed rows and how many flower parts are left over. So according to Euclid's division lemma, A is equal to BQ plus R. Total parts, how many you have? 532. That is equal to, in each row, how many flower parts? 21. Now, you have to divide 532 by 21. What it is? 25. The quotient is 25. If we divide, ordinary division, if we divide, what you will get as quotient? 25. So that is the quotient, plus the remainder is 7. So number of completed rows is 25 and the remaining flower parts left is 7. Very, very easy sum, but very, very important sum. Important 2 mark sum. Okay. So again, I'll repeat. So total parts is 532 and number of flower parts in each row is 21. So you divide 532 by 21. The quotient is 25 and the remainder is 7. So this is the number of completed rows and this is the remaining flower parts. That's all. Then the third sum. Prove that the product of two consecutive positive integers is divisible by 2. So here you have to take two cases. In the first case, let the first number is even number. So even number means it should be a multiple of 2 only. 2k. 2 ones are 2, 2 twos are 4, 2 threes are 6 like that. So the second consecutive number means the number after the first number. That is called consecutive number. 2, 3, 4, 5, 5, 6, 8, 9. Those are called consecutive numbers. So the immediate consecutive numbers. Okay. So the second number is odd. If the first number is even, for example, if I take 2, what will be the second consecutive number? 3. That is odd number. In the same way, here we have taken this one as 2k. So the next odd number is 2k plus 1. Now we have to find the product. So 2k into 2k plus 1. So here, since this one number has 2, it is divisible by 2. Obviously, it is divisible by 2. Since you have 2 outside, no, it will be divisible by 2. Second case, the first number is odd. So if it is odd, even means 2k, odd means 2k plus 1. So what is the next number? 2k plus 1 plus 1. Again, you have to add one more number. 1 to the number. So 2k plus 1 plus 1. It is 2k plus 2. So the product is 2k plus 1 and 2k plus 2. I am taking this one 2 outside. Here I am taking 2 outside. So what is that? K plus 1. That k and that 2 I am putting here 2. So if I take 2 here, the first term will become k and the second term will become 1. So this is 2 into 2k plus 1 into k plus 1. Since you have 2, it is divisible by 2. Now the fourth sum. When the positive integers a and b are a, b and c are divisible divided by 13, the respective remainders are 9, 7, 10. Show that a plus b plus c is divisible by 13. Here you have a is given as 13 divisible by 13. So it is multiple of 13, 13k. So it is given, leaving the remainder as 9. So you have to add plus 9. Then the second number is again 13. Again one more, this one number divisible by 13. Yes. So you are taken this one as 13m plus the least the remainder as 7. So 13m plus 7. Another number is 13n plus leaves the remainder as 10. So 13n plus 10. Now what is a plus b plus c? I am writing this one 13k plus 9, 13m plus k plus 7 plus 13n plus 10. Now 13k, 13m, 13n. If I add this one 9 plus 7, 60 plus 10 is 26. Now for all these numbers, I am taking this 13 outside. So what inside the bracket, what you have? K plus m plus n. So here also, all these numbers, this is also multiple of 13, no? So plus 2, this bracket won't come. K plus m plus n plus 2, then only the bracket will end. A plus b plus c is a multiple of 13 now, yes? So it is divisible by 13. Then the fifth sum, prove that the square of any integer leaves the remainder either 0 or 1 is when divided by 4. Let the integer be even. Here it is given the integer be even. So we can take x is equal to 2k. Whenever it is given, even means you have to take the number as 2k. Now what is x square? 2k the whole square. 2 2s are 4, k into k square. Now since it is 4k square, it is multiple of 4. Then therefore when divided by 4 leaves remainder 0. So since it is a multiple of 4, for example, if I take 12, 12 divided by 4 is, what is the quotient? 3 and the remainder is 0. So if a number is a multiple of 4, then when divided by 4, it leaves the remainder as 0. Now let the number be odd. You can take the number be odd. So you can take, instead of x, you can take y. Y is equal to, even means 2k, odd means 2k plus 1. Then y square, 2k plus 1 the whole square, a plus b the whole square, a square, 4k square plus 2ab, 2 into 4k into 1. 2 into 2k plus 1 into 1. So it is 4k plus 1. I am taking 4 outside. So this is k square. If I take k 4, what it will be? K plus 1. So when divided by 4, it leaves the remainder 1. Because this number will be divisible by 4. And you will get the remainder as 1. Now sixth sum. Use Euclid's division algorithm to find the highest common factor. So here it is given, you use Euclid's division algorithm. So you have to follow this Euclid lemma. A is equal to BQ plus R, that to be followed. So first you take 340 and 412. Always you take the greater number first and write the second number 340, divide 412 by 340 one time and the remainder is 72. Now you take this one 340, divide 340 by the remainder 72. How many times 72? 4 times. And the remainder is 52. Now you take this 72. 72 equal to, divide 72 by the remainder 52. How many times? Only one time. The remainder is 20. 72 minus 52 is 20. Now you take 52. How many times? Divide the 52 by 20. So 2 into 20 is 40. The remainder is 12. Now you take this one 20 as the divisor. This is the remainder. How many times 12 is there? Only one time. So the remainder is 8. Now you take this 12 and this divide by 8 only one time and the remainder is 4. Now we take this one 8, 4. 4 2s are 8. Okay, remainder is 0. So the HF is 4. Take the second sum. 867 and 255. Again, by Euclid's division algorithm, first you take this one 867 and 255. Divide this one by 255 3 times and the remainder is 102. Now we take 255, divide this one by 102 2 times. So 2 times and the remainder is 51. Now we take 102 and the remainder 2 times. Remainder is 0. So HCF is the last divisor 51. Then 10,224 equal to, you have to find these two numbers. HCF of these two numbers only one time. The remainder is 576. Then you take this number 9,648 divided by the divisor 576 16 times. If you divide 16 times and the remainder is 432. Now you take 576 and divided by the remainder 432 only one time and the remainder is 144. Now we take this 432 and the divisor and the remainder 144 3 times. The remainder is 0, so the HF is 144. The last sum 84, 90, 120. First you take 90 and 84, these two numbers. 90, divide 90 by 84 only one time and the remainder is 6. Then take 84 divided by the remainder 6, 14 times plus 0. So the HF is 6. Now we take the 6 and the last number 120. So divide 120 by 6 20 times, the remainder is 0. So the HF is 6. Seventh sum, find the largest number which divides 1230 and 1926, leaving remainder 12 in each case. So if you are having reminders, that to be subtracted from the given number. So you take the first number 1230 minus 12, it is 1218. Then 1926 minus 12, it is 1914. So you have to find the HCF of these two numbers. 1919 equal to 1218 only one time, and the remainder is 696. Take this number and the remainder is 696. If you divide by the remainder, you will get the quotient as 1 and the remainder is 522. Now we take 696 and the remainder 522. How many times? Only one time, and the remainder is 174. Now we take 522 and the remainder 174. How many times? 3 times. So the HCF is 174. That is the answer. Then eighth sum. Find if D is the highest common factor of 32 and 60. Find X and Y. Satisfying D is equal to 32X plus 60Y. So you can take this 60 equal to, so here 60 equal to 32. 32 into 1 plus, what is the remainder? Only one time 28. Then now you take this one 32. 32 is the 32, divide 32 by the remainder 28. Only one time, remainder 4. Then you take 28 divided by the remainder 4 7 times plus 0. So the HCF is 4. But D is given as 32X plus 60Y. So D is the HCF. So 4 is equal to 32X plus 60Y. So 4 is equal to, in the place of X, substitute the value. So here 4 is equal to 32 minus 28 here. 32 minus of, so here 60 minus, how to write? 32 minus 28. So 32 minus, this one can be written as 60 minus 32. This 28 can be written as 60 minus 32. Now 32 multiply by the minus. So it is minus 60 minus minus plus 32. So 32 here, if I take this 32 and 32, 2 times 32 plus 60 into minus 1. So our aim is to find out this X and Y, no? So we are going to express this one in the form of BQ plus R, A into BQ plus R here. So it is 4 is equal to 32 minus here. Okay. So here 32 into 2 times, no? Here this is X is equal to 2 and Y is equal to minus 1. Ninth sum. A positive integer when divided by 88 gives the remainder 61. What will be the remainder when the same number is divided by 11? So A is equal to BQ plus R. So A is equal to, so when divided by 88, so the quotient is this one 88 divided by 88 Q and the remainder is 61. So A by 11, that is the remainder. Okay. Now 88Q plus 61 by 11 here equal to, you have to find out this one. A is equal to this one. So A by 11 we are going to find out. So this is 88Q plus 61 by 11. 88Q by 11 plus 61 by 11. So here what it is? If I cancel this one, this will become 8Q plus 61 by 11. So 61 is equal to, outright 61, 11 into 5 plus 6. Okay, 61 is 11 into 5 plus 6. So the remainder is 6. That only asked. Then prove that two consecutive positive integers are always co-prime. So let the numbers be n and n plus 1. A is equal to BQ plus R. So n plus 1 is equal to n into 1 plus 1. So here n is equal to 1 into 1 plus, if this one goes to the other side, it becomes 0. 1 minus 1 is 0. So the HCF is 1. Therefore, n and n are co-prime. Okay. So that's all under this exercise.